today, we're hanging out with Melinda Webster. Melinda is a polar scientist at NASA's Goddard Space Flight Center. Her work uses a combination of satellite, airborne, field, and model data to study the frozen oceans in the Arctic and Antarctic environments. So she's been involved in several polar expeditions, traveling by aircraft, ship, and snowmobile to collect measurements of sea ice to better understand its role in the Earth's systems. From growing up in small town Oklahoma to being frozen in the middle of the Arctic Ocean, she loves to inspire students to break norms and reach for new possibilities. So Melinda, it's so great to be stealing a little bit of your time today. We're gonna look forward to learning a little bit more about you, and then we'll let the classrooms take it away with some Q&A action.
Fantastic. Thank you so much for having me. I'm really excited to highlight some of the work I've been doing. So let me just get that started right away. Okay, just let me know when you see my screen.
All right, we're nice and full screen.
Okay, great. All right, so I would love to share with you what it's like being a polar scientist at NASA. As you'll see, it's not a clear-cut path, and there's a lot of ways to get to something like this. So before we begin, I'd like to tell you a little bit about myself. Who am I? My name is Melinda. I am a polar scientist, but I've not always been a polar scientist. I actually grew up in Oklahoma. I spent the first 20 years of my life there, and I was not doing any polar science there. In fact, I didn't really do anything involving climate change or science in general. What changed that was I got to volunteer with some scientists and learn about their work, and that motivated me to go back to school and finish my degrees in Seattle. So this was at the University of Washington, and I was learning about oceanography there. And from there, I got involved in polar science, specifically sea ice research. I got a position at NASA's Goddard Space Flight Center just a few years ago, so I made the big leap from going from Seattle to near Washington, D.C. to start my job as a polar scientist. So what does a polar scientist do? That's a really funny question to ask because a lot of people have different expectations of what we do. My mom thinks I'm like Bill Nye the Science Guy. I'm not. Society thinks I'm kind of like a mad scientist. I'm not that either. My boss probably thinks I'm a walking disaster. So there are all these perceptions of what scientists do, and some of them are right, some of them are wrong. What do I actually do? So this is a really nice graph that shows that. My job is a combination of things. So the big part of it is being creative, coming up with new ideas and new interpretation, and reading and writing. That's what I do for the vast majority of my time. The other part of my time, I'm analyzing data. I'm crunching numbers. I'm using math and science to do this, but it turns out you don't have to be an expert in math to do this, which is great because I'm not. The other part of my work is more working with teams, so networking, being on a field expedition and working with others. And that's really my favorite part of my job, is getting out in the field and being able to work with others. The last part of my job is I do a lot of public service. So what does this mean? It means talking with folks like you about the work that I'm doing, but it also means meeting with politicians and showing why science is so important and why we need to pay attention to the ongoing changes on our planet. So in summary, that's what my job's about. But now let's talk about the fun part, the science. So I studied the cryosphere. And the cryosphere is actually a really easy thing to define. It is the frozen parts of our planet. And when you stop and think about that, the frozen parts of our planet are everywhere. They're not just in polar regions. They're on every continent of our planet. And this is really cool. But it's not just limited to the continents. It's constantly changing. You know, you'll have a lot of snow in winter, and then you'll have no snow in summer. The cryosphere expands and contracts with the season. It's constantly evolving over time, over short time periods, like on a seasonal basis, to really long-term trends, like the loss in Arctic sea ice and the North Pole environment. So this is good to keep in mind when you hear the word cryosphere. This is what it entails. Now, the cryosphere can be defined a little bit differently in saying, okay, well, there are two parts of it. There is the snow part, and then there is the ice part. That's easy to think of. And my area of expertise is on the ice, but it turns out not all ice is created equal. It's not all the same. You have ice that comes out of your refrigerator that you put in glasses of water. That's freshwater ice. The thing that I care most about at the moment is sea ice. This is the frozen part of the ocean. And in today's talk, I'm going to try to convince you that this is the coolest type of ice ever. Okay, so why is it so awesome? Well, I think if you had to step back and say it, it's really the key thing that regulates our climate. It does a number of really important things for the Earth system to help maintain a habitable place and to make sure that we're not too warm and we're not too cold on this planet. So what does it do exactly? Well, its superpower is its high albedo. And albedo is a way to describe how much sunlight is reflected back into space. So we have an example here where you have an ice-covered area. It reflects about 70 to 80% of the light back to space. That's a really large amount. Compared to the ocean only reflects about 7%. So that's a huge difference. That's like wearing a black shirt or a white shirt in a sunny desert. You would much prefer wearing a white shirt so it's not so hot versus a black shirt which is absorbing a lot of sunlight and making you too warm. That's what sea ice does for our planet. Now, it's also important outside of its albedo effect. It's also really important for regulating where our planet warms and where it cools off. So in this figure, I'm showing what the temperature is on our entire planet. The blue colors are where it's cold, the red colors are where it's warm. Because the ice is so reflective, this is helping cool our planet at the poles where it's really important too. Okay, there's also some other things that make sea ice really important, and this has to do with our oceans. So they're one of the big drivers of our ocean currents, and a lot of people are surprised to hear this, but sea ice does two things for our circulation of our oceans. One is that it cools seawater, and colder water is denser or heavier than warmer seawater. And the second thing it does is it makes seawater salty. Salty water is heavier than fresh water, so this causes these water masses to sink and to create this convection, this overturning of the oceans. And that's really, really important for transporting heat to all the right places on our planet. Now, there's one last thing that makes sea ice amazing. And I'm going to play a video, and I want to see if you can see what's going on. It's really unique, and a lot of people tend to overlook this about sea ice. Oops, let me go back. Hang on. Okay, so in this video, which I hope you're seeing, you'll see this little blob moving around. This is a picture of sea ice, and that blob is a living thing in the ice. The reason this is incredible is that this is proof that life can live in an extreme environment like the ice itself. And this gives us clues to what could be happening on other planets and moons outside of the Earth system. So if we're trying to find life on other planets or in other places in the universe, the sea ice environment is a perfect case study to see where they might be living. And that is pretty amazing in itself. Okay, so how do we know all of these fascinating things about sea ice and what's going on with it for climate and what's going on with it for life forms? Well, we go out on the ice, from the boots on the ground to flying in aircrafts to launching satellites into space. We use all of these different ways to measure the ice and different time scales and spatial scales to get as much information as possible. And that's what we really need to do to understand how it works in the Earth system. So one of my favorite things to do for my job is to take an aircraft to high latitudes to take measurements of the ice cover. So we equipped the airplane with a lot of snow thickness and ice thickness instruments. And these are really important for monitoring the changes happening in our environment. So we've seen it loss of sea ice over time. The planet is warming, especially in Arctic environments. It's warming more rapidly than anywhere else. So we're having a lot thinner ice and less extensive ice. And these airborne surveys are really important for gauging that change. Another way that we do it is we go out in the field, but this is extremely risky. So doing field work is challenging. It's an extremely remote environment. So when things go wrong, there's nobody there to really bail you out or help you. It can be really dangerous. The ice can break up. You can fall through the ice if it's too thin. There are polar bears, and those are dangerous. And of course, it's really, really cold. You can get hypothermic, and that can be scary. And oftentimes with these fieldwork expeditions, we only get one shot to get things right. We don't get to do a repeat usually because we just don't have the money to. That's the way things work. So why are we doing this? Why do we take all these risks to go out and try to take measurements? Well, there's a lot of good reasons, I would say. For me personally, it's an adventure. I love going out in the field and learning new things. You know, when you're curious about how the Earth works and what's happening in these environments, being out there is so informative and exciting. And I think what's often the biggest reason to go out and do field work or airborne campaigns or satellite missions is this is really where the groundbreaking discoveries happen. This is enabling new science to be done, and it opens up our understanding in ways that were never possible before. Okay, and then on a personal note, when you're out in the field, your colleagues become family because you're there for months on end. And this is really cool because I can't imagine going out in the field with anyone else than my colleagues. They're wonderful people, and it just makes it so much fun to do this work. And summarizing all of these points together, this really makes this job a passion, and I feel very lucky to do what I'm doing. And I think it would be great for anyone else to get involved if this sounds right up their alley. Okay, so with fieldwork, how do we actually get out in the field, and how do we prepare for these expeditions? There's a lot of things that could go wrong. There's a lot of risks involved. So how do we do it? Well, we come up with a plan, and we have lots and lots of backup plans for when things go wrong. So we have to coordinate what types of instruments are we going to be using? Do we have redundancies in place for when things break? So we might want to bring double the amount of instruments that we need because the first set of instruments may not last as long. We need to identify who the key players are on our team. It's kind of like assembling a sports team or a baseball team. How are you going to choose your all-star team to be successful? You want the expert at pitching. You want the expert at modeling. You know, you want to assemble the strongest team ever so you can be successful in what measurements you're trying to make and conclusions that you're trying to draw. Okay, and then there are some other elements to fieldwork and airborne missions that take place. So identifying what time of year we want to go take measurements, how long we're going to spend in the field, and how much is all this going to cost? Because it can be really competitive to put these ideas together. It has to undergo review. So you don't want to be too expensive. You don't want to be too ambitious. You want to have the perfect Goldilocks scenario where it's not too much and it's not too little. It's just right so somebody thinks it's a solid, doable idea. Okay, so when we're actually out in the field, it can be really difficult. So I often go out in the springtime where it can be minus 40 degrees Fahrenheit, which is the same as minus 40 degrees Celsius at that point. It's just really cold. And it can be difficult to do a number of things simultaneously. So the first three things that I try to do is to stay warm, to breathe, and to see. And it's really hard to do all those three things at once. So in the picture in the upper right, you'll see that my face is all frosted over. That's because I'm trying to stay warm and I'm breathing hard, but my goggles are getting all fogged up. So if I take them off, then I can see, but then I get cold. So it's just this reconfiguration of trying to do all these things at once that you get used to after a while, but it can be hard. Bringing snacks out into the field, you know, they freeze immediately. So you have to keep things close to your body. batteries and things like that, you have to keep close to your body so they don't get frozen. And so you want your instruments to work. At the end of the day, you really want to get good data, but you also want to be safe. So you're constantly assessing the risk to make sure you're not making a bad decision. Okay, so how do we do this as a team? Well, it really goes back to what you learn when you're really young. You're taught to help others. You're taught to pick up the slack. You're taught to communicate. All of these things are really, really important to being a successful team player in a field expedition, an airborne mission, or a satellite mission. And at the end of the day, it's really important to have fun because we're all human and we're all doing this because we love the work. So it's nice to have fun with it. But I think probably one of the biggest secret weapons to success in the field is candy. This is a great way to make friends, and it's actually a really effective way to boost morale when you're out on the ice for months on end. These little things make a big difference and help your relationships with others. Okay, so after we go on a field campaign, we get to go home happy, but then what happens? Well, the biggest thing is analyzing the data and making discoveries. So the biggest part of my time is spent reading and writing and coming up with new hypotheses and crunching all of these numbers that we collected and trying to make something meaningful and important out of them. So for my work in particular, I've done a full range of stuff where I've been looking at cyclones and storms and seeing where they go in the Arctic. I've been looking at the temperature of the ice and how that evolves over time, going from winter into summer, seeing how quickly it melts and how it's changing. And on the upper right, I've been looking at changes in snow depth on sea ice. So we were able to tie in all these different measurements for a really long time period to see how the snow cover has thinned over Arctic sea ice. And on the bottom right, and this is something I'm pretty excited about, is working with artists to put our science into a beautiful image. How can we take all these numbers and all this dry information and make it really exciting and visually appealing to different people? And so this figure is just showing how complex snow on sea ice can be for the Earth system. And all of these components come together to tell powerful stories about sea ice. So that's something that really excites me in particular about my job is we take all of these numbers and we learn something new. Everything that we're doing, all the measurements we take out in the field are the first of their kind, and it's always adding something new and positive to our understanding of sea ice and Earth as a system. Okay, so that's all I have. I really appreciate you paying attention. I'd love to hear your questions about this work, so thank you.